Ever bought a brand new phone, unboxed it, and powered it on for the first time, and it just works? Felt magical, right? But have you ever wondered what happens to a chip between the moment it's etched onto a silicon wafer and the moment it lands in your hands? Because a lot can go wrong in between. And here's the thing, the last two steps before a chip ships, testing and packaging, are just as critical as the billion-dollar machines that made it. So today, let's crack open that black box and see what really happens. Let's start with testing. When a chip is still part of a wafer, that big, thin disk of silicon, it's not yet a finished product. It's one of hundreds or thousands of identical little rectangles living together on that wafer. And some of them, inevitably, are duds. That's where wafer sort comes in. Think of it like quality control at a bakery. Before you box up the croissants, you tap each one to see if it's hollow or burnt. With chips, a machine prods each tiny die, that's the chip's official name, while it's still on the wafer, with electrical signals. It checks if the logic gates fire correctly, if the memory cells hold data, if the clock speed is stable. Any die that fails gets marked with a tiny drop of ink, or more often, a digital flag sent to a database. Later, those bad dies get discarded. It's brutal but efficient. You don't want to waste time packaging a chip that's dead on arrival. But wafer sort isn't the final test. Once a chip survives the sort, it gets cut out of the wafer, a process called dicing, which is basically a super precise diamond saw, and then it's ready for packaging. Now, packaging is where the chip transforms from a fragile sliver of silicon into the robust black square you see on a circuit board. Why does it need a package? Two reasons: protection and connectivity. The chip itself is delicate, a single scratch or speck of dust can kill it. The package shields it from the outside world. And those tiny input-output pads on the chip are microscopic. You can't solder them directly to a motherboard. The package fans them out into bigger, easier-to-handle pins or balls. There are several common packaging types, and they matter for different jobs. The simplest is QFN, short for Quad Flat No Leads. That's a small, rectangular package with metal pads on its bottom. You see QFNs in things like power management chips or simple sensors. They're cheap and compact. A step up is BGA, or ball grid array. Instead of flat pads, a BGA has hundreds of tiny solder balls arranged in a grid on the bottom. When you heat the chip, those balls melt and connect to the board. BGAs are everywhere in modern electronics: your phone's processor, your laptop's graphics chip, your car's infotainment system. They can pack more connections than QFNs, so they're great for complex chips that need to talk to lots of other parts. But here's where it gets really interesting: advanced packaging. You might have heard the term chiplets or 3D stacking. This isn't your grandpa's packaging. Traditionally, you put one chip in one package. But with chiplets, you break a big, expensive chip into smaller, specialized pieces, like a brain made of separate modules for computing, memory, and graphics, and then glue them together inside a single package. Why do that? Because making one giant chip is harder and more expensive. It's like building a house. You can try to carve one massive block of stone into a kitchen, bedroom, and bathroom. Or you can build those rooms separately and connect them with hallways. Chiplets are those separate rooms, and advanced packaging is the hallway. AMD's Ryzen processors use chiplets, so do some of the latest AI accelerators. Then there's 3D stacking. Imagine taking two chips, say, a processor and its memory, and stacking them on top of each other, connecting them with vertical channels called through-silicon vias. That's 3D stacking. It shortens the distance data has to travel, which means faster performance and lower power consumption. Think of it like moving from a sprawling ranch house to a high-rise apartment. Everything's closer together. Companies like Samsung and TSMC are investing billions in this technology because it's the only way to keep shrinking chips without hitting physical limits. Now, a common misconception: many people think packaging is just a boring, low-tech afterthought, the shrink wrap of the chip world. But that couldn't be further from the truth. In fact, advanced packaging is now a bottleneck for companies like Nvidia and Apple. They can design the world's best chip, but if they can't package it properly, if the heat dissipation is poor or the connections are too slow, the whole product flops. That's why TSMC's CoWoS packaging line has been in the news. It's not just about making chips, it's about how you put them together. And because it's so complex, there isn't enough capacity to meet demand. So packaging has become a strategic battleground, not a boring afterthought. To wrap it up, testing catches the bad chips early, packaging turns fragile silicon into a tough, connected component. And advanced packaging lets us build chips that are faster and more powerful than ever, by combining chiplets or stacking them in 3D. It's the final magic trick before the chip goes to work in your phone, your car, or your data center. Next time, we'll zoom out and answer a fundamental question: what is a wafer? And why its size and defects matter, because without that round slice of silicon, none of this exists. Subscribe to Taiwan Tech Pulse for more Taiwan Tech 101.